So let's remember when we're talking about acids, to be a strong acid or a strong base, it means you dissociate completely. That means that the equilibrium lies far to the right and the reaction essentially goes into completion, meaning that, for example, HCl, you have no HCl molecules left over. They're all H plus ions and Cl minus ions floating around in solution. That's what it means to be strong. When you are a weak acid, essentially the equilibrium lies to the left. So remember, a weak acid is abbreviated HA. We'll do this one where we include the water. The double arrows mean that this is a reversible equilibrium. In this case, most of them lie to the left. They favor the reactants. Water is going to act as a base in this situation, and it will receive or accept a proton from the weak acid, leaving behind its conjugate base. The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. So this is an equilibrium problem, so we're going to do an ice chart. We'll put the initial concentration here. Water we will ignore. These always get 0 before we start because this is before dissociation occurs. Some of it's going to fall apart into one piece of each. Remember, dissociation is stepwise, so you're never going to have any coefficients in these. So all of the problems are going to look very similar. Let's remember that because these are weak acids, this contribution is usually so small that it doesn't really change the initial concentration. So we do ourselves a favor and ignore that. So the Ka becomes x squared over initial concentration every time. Then remember that x value gives us the concentration of H plus from right here. H plus, H3O plus, we're going to use them interchangeably. Then to get the pH, we take the negative log of the concentration of H plus, so it's going to be negative log of X. So now we've calculated the Ka, we've calculated the pH of the solution. They might also ask us about the percent dissociation. So the percent dissociation is how much of it falls apart compared to how much of it stays together as a molecule. So that's going to be the amount that is H plus or A minus over the amount that stays as HA. So that's basically going to be the value of X over the initial concentration times 100. Those are all the things they might ask you and how to calculate them. Let's see, they did go crazy and asked you for Kb though. We remember that Kb times Ka is equal to Kw. Kw is always 1 times 10 to the minus 14. So Kb we could calculate by taking 1 times 10 to the minus 14, which is Kw, over the Ka we just calculated. If they ask for POH, you'll remember that POH and pH added together always equal 14. So we can say that POH is 14 minus the pH, which we calculated above. If they asked you for concentration of the OH, remember the concentration of H plus is our X value. Concentration of OH times concentration of H plus is always equal to Kw. So 1 times 10 to the minus 14. So I could do concentration of OH minus equals Kw over the concentration of H plus, which is X. You could also do the POH. 10 raised to the negative POH will also give you the concentration of H plus. So that's a brief summary of how you do weak acid problems, what they might ask you, and how you would complete them. Now we're going to generalize weak bases, which are abbreviated B. When you put a weak base into water, it will provide us OH. And there's not going to be an OH in a lot of weak bases, so it's going to be confusing to you. But if you remember, always remember, acids donate H pluses or protons. Bases accept them. So what's going to happen if something is going to be a base, it's going to be electron rich, and it is going to accept a proton from water. After it accepts a proton from water, it's going to leave behind an OH minus. Water is essentially an H plus and an OH minus put together. So acids will always pluck off the OH to leave behind H plus. And bases will pluck off the H plus to leave behind OH minus. Okay, let's draw our chart here. So ICE, we'll put our initial concentration here. Again, we're going to ignore water, and these are 0 before we start any dissociation. You'll get one piece of each of these. This is always going to be the case. And again, this contribution here for a weak base is going to be considered small, so we're going to ignore that. We expect the value of X to be so small that it doesn't change that value on the bottom of initial concentration. In this case, be careful because X is going to give us OH minus. So when you're doing our problems here, you're not solving for Ka, you're solving for Kb. So have OH minus remind you of base and know that we're solving for the base dissociation constant. So my Kb becomes X squared over initial concentration. My X value in this case is not H plus. My X value is the concentration of OH minus. So this time the POH is negative log of X. Once we have the Kb, if we want to find the Ka, Ka times Kb is always equal to Kw, which is 1 times 10 to the minus 14. All these equations are in your reference packet for you to be using, so you can always look them up. I now can calculate, I've calculated Kb, I've calculated the concentration of OH minus, I've calculated POH, now I have Ka. If I want pH, all I have to do is take my POH and subtract it from 14. That will give me my pH. And if I want my concentration of H plus plus OH minus, H plus times OH minus always equals 1 times 10 to the minus 14. So H plus would be 1 times 10 to the minus 14 over the concentration of OH minus. So there's just a summary of what we learned yesterday on how to do any of these equations. They might ask you to, let's just add this in here like we did for the base. For the acid, if they're looking for percent dissociation, you're going to take the value of X over the initial concentration times 100, just like we did with the acids. I will post this, so in case you ever need to refer back to it, it's right there at your fingertips. I tried to be quick in going through this, so in case you have to watch it again, it's not going to be a 20-minute video.